Well, all right. Welcome back. The jacket's coming off. I'm sweating up here because last lecture was, I think, frustrating for some individuals. So I will warn you to take a deep breath and hang on because this one's a doozy. In part because we're putting together a lot of things in ways that you maybe haven't done so yet, but which really test how well you've mastered a bunch of different reactions. I want to start out just real briefly giving you, maybe 10 minutes of what we need to know from Chapter 11. All right? I don't like Chapter 11 very much, in part because some of the mechanistic details are complicated enough that they're beyond the scope of an undergraduate class. So, and the other thing I don't like about Chapter 11 is that it presents reactions with alkynes as though they're separate and maybe different from what you did in Chapter 10. And they're not. They're exactly the same. The only difference is that, sorry, I'm getting emails and it's showing up on the screen. There we go. The only difference is that you're dealing with an alkyne that has 2 pi bonds instead of an alkene that has 1. So, for example, in Chapter 10, we did hydrohalogenation, where you would take an alkene and you would add HBr, and you would get the alkyl bromide as your product. If you use an alkyne, I'm sorry, I think I wanted to choose a starting material that was a little bit more complicated. I hope you'll forgive me, because this gives us a chance to deal with regioselectivity. The bromine ends up on the more substituted carbon because you have a carbocationic intermediate, and that's where the carbocation is more stable. That's Chapter 10, and that should hopefully be familiar to you. In Chapter 11, if you add HBr, and let's say we're just adding 1 mole of HBr for every mole of this, what we're going to call a terminal alkyne. That is an alkyne that has a proton attached to one of the carbons. We're going to do exactly the same thing. The bromine is going to end up on the more substituted carbon because of the presence of presumably a carbocationic intermediate, and the carbocation's more stable on the more substituted carbon, and then bromine will attack that more substituted carbon. Mechanistically, I'm not going to ask you to draw the mechanism for this reaction, but it certainly would involve this kind of thing, where the pi electrons from the alkyne attack the proton of HBr. The thing that gets attacked ends up on the less substituted carbon so that the positive charge can be on the more substituted carbon. And then bromine ends up on the more substituted carbon. We got some comedy going on in the chat. This lecture is going to be alkynes of trouble. Sounds good. Oh, and speaking of comedy, I have to show you this text I got from my sons the other day. Let's see, there it is. So this is meme poetry, M-E-M-E poetry. Roses are red. I am Groot. Where is my super suit? So I don't know where he got this or whether there's more of these kinds of things, but I was pretty entertained by that. Okay, joking's over, back to business. So you get exactly what you would predict. And then if you were to add another equivalent of HBr, it's going to happen in exactly the same way as we do hydrohalogenation of alkenes. The pi electrons attack the hydrogen of HBr, bromine leaves. You create a new carbon-hydrogen bond with the less substituted carbon, so that the more substituted carbon can have the positive charge, and then bromine attacks the more substituted carbon. And you end up with this product, which is called, and you don't need to memorize this, a vicinal, nope, actually, It's not vicinal, it's geminal. That means bromos on the same carbon. Geminal dibromide, from the Greek Gemini for twins. And another reason that the bromo ends up on the more substituted carbon is because the positive charge is better when it's adjacent to bromine, because it's resonance stabilized. The lone pairs on the Br can kick down and delocalize that positive charge. All right? So the difference here is you got 2 double bonds instead of 1, but in terms of the details and the mechanism of the reaction, you can think of it as exactly the same. I will specify whether we're just adding 1 equivalent or 2 equivalents of HBr. I will point out that if your alkyne is a little bit more complicated, that is, if it has 2 non-hydrogen things attached and the 2 non-hydrogen things are different from each other, you're going to get 2 possible products. One in which the 2 BRs are adjacent to the R group, and the other in which the 2 BRs are adjacent to the R prime group. All right. So there's not really a lot to see here other than if you see a product with bromines on 2 carbons, you should be thinking, I maybe could have got that from an alkyne of some sort. Now, we can do exactly analogous things with alkynes and hydration reactions. So your text makes a big deal out of saying that for some alkynes you need to add a mercury catalyst, and we're going to ignore that completely. As before, when we did hydration of alkenes, we're going to get a product where the more substituted carbon gets the OH group. This kind of product, though, is not the final product. It is a enol, which is sort of an unstable intermediate. The enol has an isomer that is actually more stable, and it's a special kind of isomer that involves moving only a proton and a pi bond. Just to be clear, here's the proton that moves, and here's the pi bond that moved. These 2 molecules, the enol and the ketone, are a special kind of isomer. They are called tautomers because they differ only in the location of a proton and a pi bond. I won't ask you the mechanism for getting from enol to ketone. It's actually pretty easy. You just remove the proton from the alcohol of the enol, then recognize that the resulting conjugate base is resonance stabilized with negative charge on this oxygen and on this carbon. And if you protonate on that carbon, you get the ketone. The ketone is more stable than the enol because carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds. Okay, some housekeeping questions from the chat. When is test 3? It is on Saturday, the 27th. Is chapter 11 going to be on the test? Only the parts that I'm talking about now. Now, suppose instead of the ketone product, suppose you wanted the oxygen to end up on the less substituted carbon. That is, suppose you wanted to make an enol that looked like this, and then when you did the isomerization process, you would get the aldehyde instead of the ketone. Do we know of a reaction that will put an OH on the less substituted carbon of a pi bond? Sure, that's a chapter 10 reaction. This is hydroboration oxidation. Which proceeds in the same way. You have the pi bond attack the boron, and then a hydride gets delivered to the more substituted carbon, the boron on the less substituted carbon. Then in the second step, you convert the BH2 group into an OH group. Again, this is a less stable enol, which tautomerizes or isomerizes to the more stable aldehyde. This will be the first time, I think, in this class that we've made an aldehyde or a ketone. So if you see one of these as a product and you're asked to provide a reagent or a starting material, you need to start thinking, okay, aldehyde or ketone, I could have made that from an alkyne. All right, question so far? This will work better if you connect what we're seeing now with alkynes to what you learned about alkenes, if you don't think about them in separate categories. Yeah?
Does that reaction with the tautomer, sorry, is the tautomer like something you have to add, like a reagent? Or is that
no, the word tautomer describes the relationship between these two compounds. They are isomers of each other.
Okay, so that happens just kind of...
It happens spontaneously in aqueous solution.
Okay.
Yeah. And you'll learn the mechanism for this in 352. It's, as I said, it's not hard, but I think it's a detail that we can defer until then. Others? All right. Oh, sorry, go ahead.
So can you make the aldehyde out of just like under any basic addition, or does it have to be the BH3?
Can you make the aldehyde under any basic condition? No, the thing that puts the OH on the more substituted carbon is that hydroboration reaction. And you would get an intermediate that looked like this. The second step with hydrogen peroxide is an oxidation step, and you end up replacing the carbon-boron bond with a carbon-oxygen bond. Yeah. Okay. I guess lastly, of course, if you wanted to, you could do bromination reaction on an alkyne. If you used one equivalent of bromine, you would get the following molecule where the bromo groups are trans to each other. Presumably this would pass through a bromonium ion intermediate, just like with the alkene. If you added a second equivalent of bromine, that is a second mole of bromine for every mole of starting material, you could do the bromination reaction again, and that would put two bromines on adjacent carbons. It's not new, it's just two bromination reactions because the alkyne has two pi bonds. You might call this a tetrahalide. I don't know what it's good for, mostly to provide a complicated product to make synthesis questions more difficult for you. So again, it's going to work best if you put these reactions in the same drawers as you developed for the alkene reactions. Okay, what else? Anything?
I have a question.
Okay, yes, sorry, I forgot that the audio is on.
Oh, it's okay. Will these reactions usually go through two, like the one equivalent and the second equivalent? Is that really common?
Okay, the question is, will the reactions always go to two equivalents, always go to the let me rephrase that better. Is it possible in these reactions to just add 1 mole of reagent and get the product that comes from adding just 1 mole? Yes, you can stop there. If you add a second equivalent or a second mole of reagent for every mole of starting material, you can go on to the final product. So it will depend. I will always say in a predict products question, I will always say whether there are one or two equivalents of reagents for these alkyne reactions.
just kind of a follow-up on that. So does that first reaction, the first step, always go entirely to completion until that first reagent is completely used up, the alkyne? And then once it's used up, then the second reaction can start, or do they happen like simultaneously?
Okay, yeah, this is a good question. Whether the question here in class is whether the reaction is as ordered as we're pretending it is. That is, once this product forms, does any remaining reagent, so as you start to form this product, does it compete with the original starting material for the remaining HBr? That sounds reasonable. We're going to pretend like it isn't a problem. It might be. I just don't know. It's sort of a practical issue that you'd have to deal with if you ever wanted to make these in the lab. We're going to pretend and assume that these reactions work stepwise. You add one equivalent of starting material, you get to this step, you add the second, and you get there. Yeah. All right. One other thing about alkynes that I neglected to do in the first hour, and I want to show you where on earth we get alkynes from in the first place. How we would synthesize them. You can get them through a strategy that's very similar to the way that you get alkenes, that is through an elimination reaction. So if you used a really strong base, the base that your text uses most often for this purpose is sodium amide. If you use two equivalents of that really strong base, you're going to be able to do two tandem E2 reactions, and I'll show the mechanism of this. First, you eliminate this beta proton, electrons kick down to form a pi bond, and the leaving group leaves. Then, the second equivalent of base removes the other beta proton, electrons kick down to form a pi bond, and the leaving group leaves to give you this alkyne. So that's not a new reaction, and I may have shown it to you before, I can't remember, but likely you've forgotten it. But it's one of the useful ways to generate alkynes. Now you might ask, why would we bother generating alkynes? And the answer is, alkynes are starting materials for one of the only carbon-carbon bond-forming reactions that we know of. If I use a base that's strong enough, and again, sodium amide is usually the base of choice, the pKa of a proton attached to an alkyne is 25. So a base whose conjugate acid has a pKa greater than that is able to remove a proton from the alkyne. And of course, you would form the conjugate acid of the amide anion, which is ammonia, pKa 38 or something. So this is a great reaction to generate this anion. The anion we call the acetylide. It's the conjugate base of acetylene, and you can use it as a nucleophile in SN2 reactions. So I could react this with some alkyl halide to make a new carbon-carbon bond. And that's important in organic chemistry because the molecules we're interested in have lots of carbon-carbon bonds, and so every reaction that allows us to make a carbon-carbon bond increases the number of cool organic molecules we can make. All right. Anything you want to ask there? Sure.
Okay, sorry, so this is when like you react it with a nucleophile that has a conjugate acid of the pKa of 25, or the alkyne itself has a conjugate acid of pKa of 25?
Yeah, let's be clear. The proton on this alkyne has a pKa of 25. This is our base. The base removes a proton from the alkyne. And the reason it can do that is because the conjugate acid of the base has a pKa of 38. So this is just acid-base sort of chapter 2 chemistry, but it's one way, after you've made this alkyne, you can turn the alkyne, which is just a hydrocarbon, into a nucleophile that you can then use to make carbon-carbon bonds. All right, do I see other? No? Okay, at this point you're like, well, what the heck are those noon kids worried about? This has been okay so far. You ready? Like Luke Skywalker on the planet Dagobah, you tell Yoda that you're not afraid. And he says, I can't do it. You will be. Except in a creepier way. All right. So let's talk about synthesis. This is, synthesis literally means bringing things together. And in organic chemistry, we mean we're making complicated molecules from simple precursors, simple starting materials. Why do we do this? Well, first, it's a good way to test whether or not you have mastered the reactions that we're learning. Because in order to succeed at synthesis, you need to know what reagent reacts with what starting material to give what kind of product. You need to understand the stereochemical and regioselectivity issues associated with each reaction. But then it's also useful from a practical standpoint for organic synthesis is behind many of the small molecule drugs that we depend on to solve all our medical problems. Of course, a lot of the drugs that Hulu is advertising to me, I think Hulu has figured out that I am no longer in the coveted 18 to 35 demographic. So Hulu is now advertising lots of drugs for old people sicknesses and conditions, and I suppose that's appropriate. A lot of the new drugs that are coming out of the pharmaceutical industry happen to be proteins and antibodies. But in any case, every major drug company has a really strong synthetic organic area that is working hard to make new molecules that have interesting properties. So that's another reason why we show it to you. Now, most of you are unlikely to get a job as a drug developer in a pharmaceutical industry doing organic chemistry, unless you decide you want to major in chemistry and you want to go work for Steve Castle or David Michaelis upstairs and learn all these reactions. But if you aspire to be a physician someday, it might be nice to have some appreciation of the kind of work that goes into making the molecules that you're prescribing for people to take. So a synthesis problem in organic chemistry starts with the end in mind. So I'm going to draw a product, and let's see, did I do that right? Nope, I don't. No, I did. That's right, that's correct. So this is our desired product. Whoa. Sorry, struggling with font size. This is our desired product, and then you need to know what the allowed starting material is. In this class, the allowed starting material is determined by me, and it is arbitrary. I just choose a starting material that makes the problem complicated enough to allow you to really test your mastery of the material. In actuality, the allowed starting material could be anything, but the process needs to be economical, right? If you're going to make kilograms of some drug to do clinical trials, the process has to be cheap and easy. And so the simpler the starting material, often the better. Because I'm in charge, I'm going to choose our starting material as ethanol. And so the scenario here is that you've woken up on a deserted island and there's nobody there, and you're insanely bored, but you discover a hut that has a refrigerator well stocked with all kinds of things that you'd like to eat, and there's an Xbox there, and so you get bored after a while of gorging yourself on Hot Pockets and playing Xbox. And so you wander around, and in the basement of the hut is a fully stocked organic synthesis lab that has all these reagents, but the only sources of carbon that you can use are these bottles of vodka, which, having made covenants, you're not going to use to while away the time and as Jack Sparrow might do, but instead you decide to use it as your synthesis starting material. Is that far-fetched enough? All right, so every carbon in your product has to come from this starting material. We'll start by comparing the number of carbons in the allowed starting material with the number of carbons in the product. And that's going to give us a sense for, first, how many carbon-carbon bonds are we going to have to make? Those are generally the most difficult bonds to make in a synthesis, so we want to pay attention to those first. My product that I want to make has 1, 2, 3, 4, 5, 6 different carbons. And so that suggests that one efficient way of building this molecule might be to get these 2 carbons from my ethanol starting material, and then these I wanted to change colors there. Then these 2 carbons also from my ethanol starting material, and I would have had to make the bond between the purple section and the orange section. Does that sort of make sense? If all you're allowed to use is something with 2 carbons, you're going to have to connect some of those 2 carbon units. Similarly, it looks like one efficient way to do this might be to connect the 2 carbons on the end with the purple segment. All right. You have to think through this systematically and not panic, and the best way to do that is to start asking, for these new carbon-carbon bonds that I'm going to have to make, what kind of bonds are they, and do I know of a reaction or a kind of reaction that could give me that bond? So this bond on the right is a sigma bond. It's between 2 carbons, one of which is sp hybridized and the other is sp3 hybridized. So now I need to think, do I know of a reaction that gives me that kind of bond as the product? Go ahead.
We just did it, right?
Yeah. We just did it up above with an alkyne, right? This is where familiarity with reactions is really important, and actually mastery of reactions is important, because nothing's going to save you from looking at that and saying, I got nothing. And you can scramble through all the handouts that I might provide and through your textbook and through your notes. But if you haven't practiced and developed some sense and some intuition for how to make certain kinds of bonds, it's going to be hard for you to solve these problems. So you're going to want to practice this kind of thing, and there are challenging synthesis problems at the back of chapter 10 and the back of chapter 11, and there will continue to be synthesis problems moving forward. So yeah, the reaction we just showed you up above, where an alkyne, we'll call it the purple segment, acts as a nucleophile in SN2 fashion. To make a new carbon-carbon bond and to kick off Br- as the leaving group. And presumably this would be the orange section. All right, so that's progress, because we've figured out a way to take simpler starting materials and make our more complicated product. Now, we're not finished, in part because we haven't yet figured out how to connect the blue section with the purple section, and we haven't yet figured out how to get the purple section and the orange section from the allowed ethanol starting material. So we can approach this in a couple different ways. We can try to take these purple and orange sections and connect them to this starting material, or we can worry about the other bond. So go ahead.
If you treat that purple section with NH2, is that like, how can you be hydrogen specific and know that it's going to take off that hydrogen, not the other one? Is it just because of the pK of that one?
So yeah, the question in class, I think, is if you have an alkyne, you've got 2 protons. And so if I add my base and I add 1 equivalent of base, I mean, that's how I control it. I add 1 equivalent of base and then I only remove 1 proton.
Okay.
But the question, another way of looking at that question is the pKa of the first proton is 25. But once you take 1 proton off, that pKa gets really sky high, because to remove it, you'd have to have a dianion, 2 negative charges in the same molecule, and that would be pretty unstable. So yeah, you only remove the 1 proton. Okay, other questions? So let's talk about where we get alkynes from. We just reviewed that. Anybody remember? Go ahead.
I remember the text said that if you like halogenate, but like it comes from when you have the 2 halogens, right?
You want to have 2 halogens on adjacent carbons so that, and that's the reaction we talked about just a few minutes ago, where you use 2 equivalents of a strong base to do the 2 tandem E2 reactions. So we would need 2 equivalents of a strong base, sodium amide. Notice that's the same reagent for the next step. In practice, people just take this starting material and add 3 equivalents or even an excess of this base, and they get that acetylide anion. So yeah, the reaction there is just 2 elimination reactions. You remove a beta proton, electrons kick down to form a pi bond and leaving group leaves. Then you do it again with the second equivalent of base, you get the alkyne. With the third equivalent of base, you remove a proton from the alkyne, that converts it into a nucleophile, and then you can do the SN2 reaction. We're still not to our simple alcohol starting material. So where do I get the dihalide from? Give you a hint, that's a chapter 10 reaction. Give you another hint, it involves an intermediate like that. Looking familiar? Go ahead. Yeah, that's just olefin halogenation. So the alkene would be the starting material there. And then now we can ask, do we have a way of making the alkene from our 2 carbon starting material? And that is a chapter 9 reaction. And there's actually a couple of things that work there. Yeah, you can use POCl3 and pyridine to convert the alcohol into a good leaving group and then do the elimination reaction. Or you can do acid catalyzed alcohol dehydration. Typically you'd add a catalytic amount of H2SO4, and that would eliminate. Okay. So that's sort of hard to work through the first time, but this is a pathway that takes a very simple starting material and converts it into things we can do, carbon-carbon bond forming reactions. And this is the only one that we know of so far. You're going to learn tons in 352. So it would be good to sort of practice this pathway until you're comfortable with it. So we've taken the purple section and we've taken it all the way back to our allowed starting material. What about the yellow or orange section? Do we have any reaction that could connect the alkyl bromide, the orange section, could generate that from our 2-carbon alcohol. Go ahead.
Would it be just like an SN1 or 2?
Right, you'd want some kind of substitution reaction, like an SN2 reaction. PBr3 is a great reagent for that. That converts the OH into a good leaving group, and then Br minus comes in from the back and attacks to give you the bromide. So now we've got that section, and we know how to get here. All right, so this part is a little tough. We know how to connect the orange and the purple sections. Now we need to think about the connection between purple and blue. So, thinking sort of in a forward direction, you might ask, what could we do with this alkyne? And there are tons of things, but one might be to deprotonate the alkyne using a strong base so that we would have a nucleophile again. And this nucleophile could do SN2 type chemistry. Now, to simplify what we're wanting to do in making this new bond, let's ask the question, do we know of a reaction that gives us that kind of product? That is a reaction where we have a nucleophile on carbon 1 and then an OH on carbon 2.
Br2 and H2O.
So you're thinking Br2 and H2O from an alkene?
Yeah.
So let's just sort of try that out, because that would generate this kind of thing. Okay. And so let's ask, is there any way to take this and combine it with this to get this product? You're going to be tempted to say, sure, it looks great because, oh look, SN2 reaction. But there's a problem. Anybody see the problem? Alcohols have pKa's of 16. And alkynes are good nucleophiles, but their conjugate acids have really high pKa. So actually, when acid-base chemistry can happen, it is often the fastest thing to happen. So actually what would happen if we tried this is we would just deprotonate the alcohol. So that doesn't quite give us what we want. Nevertheless, it puts us close to the right track, because there's something similar, another reagent that has similar consequences, and that is an epoxide. We talked about this in, I think, chapter 9 when we talked about epoxides and how if you see the pattern of an OH group and a nucleophile on adjacent carbons, you could have gotten that by opening up an epoxide. So just highlighting the segments of our molecules. I guess we'll call this carbon 1 and carbon 2. We do an SN2 reaction, backside attack on the epoxide, leaving group leaves. That would make a new bond with carbon 1, and then carbon 2 would still have the negatively charged oxygen, which would pick up a proton from solvent or during workup. And actually, there we go. We have our product. Okay. Now, it's possible that this came out of left field for you. It's possible that, where did you get the epoxide from? I forgot that that epoxide existed. In retrospect, I want you to convince yourself now that if you see a nucleophile adjacent to an OH group, I want you to be thinking, I could have opened up an epoxide to get there. All right, questions about that? That was sort of where I lost the noon class. Yeah.
How did we get to the epoxide?
Right, good. How do we get the epoxide? Because we're not done yet. We have made the final product, but we did not yet figure out how to get those two blue carbons from starting material. But other questions about that final reaction? I guess this is the kind of thing, I mean, have you ever taken a test? Yes. And gotten a problem wrong, and then you come back and look at it after a while with fresh eyes, and you're like, oh, shoot, I thought I knew that, and actually I can see now how my answer is obviously wrong. And then, of course, next time you wouldn't make that same mistake. Synthesis is a lot like that. You can only learn it by trying it and making a bunch of mistakes, but you got to learn from that. And one of the things you can learn from synthesis is structural patterns, right? One of these is nucleophile on a carbon adjacent to an OH group. Think epoxide opening. Another structural pattern is alkyne with a bond between a carbon, alkyne with an sp hybridized carbon bonded to an sp3 hybridized carbon. I could have got that through an SN2 reaction. These are the kinds of patterns that you will start to recognize if you've practiced enough, and that will make this kind of thing a little bit easier. Any other questions before we talk about where we got the epoxide from? Yeah.
Could you review super quick of each little step that you took to get to this final product? Just kind of what was combined for it to get to where we are right now.
Okay. We started with our alcohol. We used PBr3 in an SN2 reaction to convert the alcohol into a good leaving group. We're going to use that later. We took the same alcohol and we dehydrated it to get an alkene. We brominated to get the dibromide. We did the double elimination to get the alkyne, then removed a proton from the alkyne. With that in place, we now have a nucleophile and an electrophile for our SN2 reaction, shown here, where we bring the purple and the orange pieces together. Having done that, we can remove a proton from the other proton from the alkyne to have a nucleophile, and then use that to open up this blue epoxide, and that gives us this final product. So the only missing piece now is where we got the epoxide from. Other questions? I'm worried because either I'm explaining this way better than I did at noon, or you guys are understanding it way better than they did at noon, or I'm explaining it poorly and you're not understanding it, but you're too afraid to say. So I'm not sure which it is. Go ahead.
So would you say that the best strategy to approach these problems is to like divide it into its parts that you want at the very end and then figure out how you got to that part?
All right, let me repeat that. So is the best strategy to...
Like divide it into for example, we divided into 3 sections of carbons, and then we just said, okay, how do we get to these parts? So would you do it like 3 different columns and say, these are the final materials that I want to interact with each other, and then you just figure out how you got from there?
Yeah, so the question is how best to approach this kind of problem. You can approach it from either direction. It is kind of like solving a 1,000-piece puzzle. In the end, you're going to get there. It may not matter whether you start with the pieces in the middle that have a particular color that is easy to see, or you start with the edges that have a particular shape that's easy to see. You may need to work backwards a little bit and forwards a little bit until you can connect the dots. It is useful if, once you know what the allowed starting materials are, to figure out, are there any carbon-carbon bonds I had to make? Because that's going to be the key point in whatever strategy that you do. So yeah, breaking it apart as we did here and then treating each individual piece as a separate synthesis problem is actually a pretty good way to do it. Sometimes you're going to find that things that you did to generate one intermediate are also useful to generate others. For example, if you're to ask where we got this epoxide from, well, it turns out you can get it from this alkene, which we made previously, doing this halohydrin formation reaction. Then you simply add a strong base that's a poor nucleophile. Sodium hydride is great for alcohols because H- is not that soluble, but it is very fast at removing a proton from the OH group. The resulting negatively charged oxygen then is a great nucleophile for a super fast SN2 reaction that happens in an intramolecular fashion to give you the epoxide. And we don't need to describe how to make that alkene again because we already did that up here. So this is an example of what we call a convergent synthesis. We start with starting materials, obviously. What else are you going to do with starting materials? We elaborate them using reactions to get the individual pieces we need, and then we stitch those pieces together. And that's a common strategy used in a lot of different complicated molecules. All right. There are some questions about format on the test. Yeah, it's hard to give an open-ended synthesis question on an exam. What I might do would be something like this. I would give you this starting material, and then I would give you the desired product. And then I would say, how do you get from there to there? What I would have to do is I would have to have lists of reactions. And in order for this to work, I would probably have to have, at various points, pieces that you could bring in that did not come from. In other words, it's hard to do a convergent synthesis like this in multiple choice format. What I have to do is give you a single starting material and a list of reagents. And then I have to give you possibilities A through X. Actually, Learning Suite doesn't let me do possibilities A through X. I think I have to stop at J, so a maximum of 10 possibilities. In a multiple choice question like this, it can be tempting to try to evaluate all 10 things by saying, okay, what happens if I do this to the alcohol and then this and then this and then this? And you try to do that 10 different times and you can get kind of panicked and hurried and make some mistakes. It can be better to try to approach this problem strategically in the way we did, thinking about, okay, well, 2 carbon starting material, I know I'm going to have to make a couple of bonds and then go from there. Yeah.
So each of those options for the multiple choice answers would be which of these is the best reagents used, or would you have like reagents missing that you would need in order to synthesize that, and that would mean that the answer is incorrect?
Yeah, so there's actually a lot of ways to format this. One would be to, but if I formatted it in this way, yeah, I wouldn't have missing reagents, I just have lists of reagents, and some of them would be bogus or not work, or have some incorrect or issue that would make the reaction not work. So you'd have to identify the one that works. Another way would be to actually draw out the synthesis and show intermediates along the way and have you fill in the reagents that make those reactions happen. Okay, yeah?
So with these reactions where there's like multiple steps, and we start with one starting material like ethanol, what are the rules on like what we can and can't use? I mean, because there's
Okay.
these POCl3.
What are the rules about what you can and can't use? Any reaction that works. That's the standard. The reaction has to actually work. So you can use any reaction that you've learned. There are multiple ways, for example, to get from this alcohol to this alkene product, and anything that works is good.
Okay.
All right, we'll have to leave it there because we're past time. We'll work some more on this next time.